which is 1/6. 1/6 divided by 5 times 4. And so on. So your y2 is going to be C1 coefficient, which is x, 1/6 x squared plus 112, 1/6 x cubed, 112 x to the power 4, 1 multiply x to the power 5, and so on. Okay. And your final solution is y will be equal to C0, y1 plus C1, y2. Okay? You can just plug those couple back in.
Go over one more time exactly how you got the different constants, like C3, C4, and C5.
Oh, okay.
I see the formula. I'm just trying to figure out how to use the formula.
Okay. Is this formula here? Okay. So let's say this guy here. Let's say this guy. Now C2 is still using this other formula though. It's still using this red one. Okay. C3. Now this one is n plus 2, right? And then n minus 1.
Yeah.
It's the sum of the previous third and previous second. So this C3 here, this guy is related to this two. Okay?
Yeah.
So it's the sum of those two divided by 3 times 2.
Okay.
Does it make sense?
Still no. Because, okay, so shoot, I muted myself. For this one, which concrete end are you using, and can you please walk me through each of the steps because it's just not sticking? I'm sorry.
Oh, no, that's fine. I'm using this equation. Do you know I'm using this equation?
I know which equation you're using. I'm just trying to figure out exactly which n you're using and exactly how that n correlates to each term in the equation when you plug the numbers in.
Okay. So here is n equal to 1. Okay, from here, when n is equal to 1, I have C3 equal to C1 plus C0 divided by 3 times 2. Do you see it now?
Yeah, thank you. Got it.
You got it now, right?
Yeah, it just wasn't clicking.
And then when n equal to 2 will be C4 equal to C2 plus C1 divided by 4 and 3. And you iterate like this.
Yeah, it's good. It's good.
Okay. Thanks for asking, Shannon. Any other question? No? We'll do one more example, okay? We'll try to do one more example. No questions?
Wait. Oh, sorry.
That's okay.
I was just gonna take up a little bit. Sorry.
Yeah, just let me know when you're ready then, okay?
Okay. Thank you.
Sure. Okay. This is probably the last example we are doing because we did quite a number of them already. So this is a prime here. I think, yes. Okay. So we're trying to solve this. So y double prime minus 2xy prime plus y equal to 0 will be this guy. Okay, you guys know what I did? You know what I just did? Is it okay? Do you guys follow this?
Yeah.
Okay, so we do some replacement to line all this up. Okay, this one is already good. Line those two up. Okay. When I line those two up, I'm going to end up with this. Here I replace n by n plus 2. Hopefully you understand. Oh, this one actually, can I do this? I don't have to line them up actually, because there's an x here. You multiply it together, will become x to the power n, right? So I don't need replacement for that. Okay, they are all lined up now. These two start with n equal to 0. The middle one start with n equal to 1. So I have to specify n equal to 0. Okay, when n equal to 0, you have 2 times C2 plus C0. Okay, it's equal to 0. I'm taking this out. Okay, I'm going to write one more step. N equal to 1 to infinity. Together all the like terms. Are you guys with me? So this guy is equal to 0. And also this guy here okay. From these two equations, I will be able to write down the recurrence relation. C2 is negative C0 over 2. Cn plus 2 is equal to 2n minus 1 Cn divided by n plus 2 n plus 1. Is it okay? Do you guys have any questions? Are you guys okay up till here?
Yeah.
Do I need to wait?
1 sec.
Okay. Now, this is an initial value problem. It's slightly different. So you're given this. This one is actually C0. This one is actually C1. You actually, you do not need to compute the general solution first. Unlike in the past, in other techniques, you compute the general solution, and then you put the initial condition in, and then you compute C0 and C1. In this type of problem, we can just start out with this. C0 is equal to 2, C1 is equal to 3, and then continue. Okay? So we just get the solution in one shot. What will be C2? C2 is negative C2, 0 over 2, negative 1. C3. Now C3, this guy and this guy, C3 is going to be related to C1. So you should think about this as n equal to 1, n equal to 1. When n equal to 1, this guy is going to be C1 divided by 3 times 2. Do you guys follow? Is it okay?
Yeah.
Okay, good. So C4. Now C4 is related to C2. C4 is related to C2. This is n equal to 2. So this term, now this term here, okay, and this is 4, as n equal to 2, this will be 3. 3 times C2 divided by 4 times 3. C5, n equal to 2. C5 is n equal to 3, so it will be 7. 7 times C3, 7 times 1/2 divided by 5 times 4. Okay, 7 over 40. And you can keep going. Okay, we do one more term. In the test, I will tell you how many terms you stop. Okay, so C6 will be, the pattern is, this is, the next one is going to be, oh, this should be a 5, sorry. That should be a 5. Okay. Because n equal to 3, right? 2 times 3 is 6, 6 minus 1 is 5. I did it wrong. So this is actually 1/8. So now C6 is n equal to 4. So this will be 7 times Cm, it is 2 earlier. 2 earlier is negative 1/4 times 6 and 5. Basically, this is just arithmetic now. It's just basically using this equation and keep plugging it. So what do we get? Minus 7 over 120. And you keep going. So now I have my answer. My answer is y equal to 2 plus 3x minus x squared plus 1/2 x cubed minus 1/4 x to the power 4 plus 1/8 x to the power 5 minus 7 over 120 x to the power 6 and so on. Okay. So in an engineering application, you can just compute as many terms as you want to get a better approximation. Notice that in this particular problem, I don't even find the general solution first. Okay. I just starting with the initial condition, which is C0 and C1, and then iterate on it. Okay. Are we doing all right? Are we doing okay?
Still finishing up some of the writing, but I'm good whenever. I took a photo of this.
Okay. I'll just wait a little bit after you guys finish writing this up or taking picture, screenshot or something. And we are then going to go to chapter 7. Are you guys ready? Or you need a little bit more time?
1 sec.
Okay. Let me know when you guys are okay.
You're good.
Okay.
Thank you.
Sure. It's called Laplace Transform. Probably completely new to most of you. Okay. In engineering, there are a lot of different transforms. Fourier transform, Laplace transform, Z transform. All those are actually related. They're all similar. Okay. So for us, we are going to focus on this thing called Laplace transform as a way of solving differential equation. Okay. So you have a differential equation. This is essentially what we do. You do Laplace transform. Laplace transform usually this cursive L stands for Laplace transform. You turn it into an algebraic equation. Okay. And then you solve the algebraic equation. After you solve the algebraic equation, so you have the algebraic solution. And then you go backwards, doing the inverse Laplace transform, then you get solution to the differential equation. Okay. So instead of solving it, usually all this other stuff we talk about, we are solving it this way. Now we're going to get a detour. You go Laplace transform, go to something algebraic. Then you don't have to do derivative and all this stuff. And then you solve it. And then you do the inverse transform. And then you get the solution. So instead of going through this blue arrow, we go through this round trip. Okay? So in some sense, you're saying that this is very nice. I don't have to do that much. It becomes an algebraic equation. The problem is it's not completely free because when you do this, you have a lot of partial fractions to do. Mean partial fractions. Okay, so essentially you're doing this at the expense of, instead of solving it directly, use a lot of partial fraction stuff, Laplace transform, and do it in an indirect way. There are other advantages in addition to this advantage, which we will talk about as we go deeper into this. Any question about this? This is kind of just it's an overall idea of what this is all about. It's kind of strange if you haven't seen it before. Okay? You guys understand this picture I'm talking about? At least on the high level? This is the Laplace transform of the function. Okay? It's defined as this integral. Provided the integral converges. Because this one is actually a improper integral, okay? So we have to make sure it converges. So in the region of convergence, so this is defined, okay? So Laplace transform of a function. So the Laplace transform will transform one function into another function, okay? This is a function, originally it's a function of t. T stands for time. And this one will be a function of what do you think it's a function of? T becomes the dummy variable in the integration. And there's a variable s here. This becomes a function of s. Okay? So basically over here, on the left-hand side, we call this the t domain or time domain. On the other side, we call this the s domain or the transform domain. So you operate over here usually, but now in this chapter we just move it over here, operate in the s domain. solve algebraic equation and then move it back. So we are going to do some examples based on this definition. Any question?
Just clarification, it's e to the 5t or e to the st?
S.
Gotcha.
It's S. It's not it's not a number. It's this S here. This S. Okay.
Thank you.
Sure. This is the Laplace transform of 1. The constant function. This is a function constantly equal to 1. What is the Laplace transform of it? Based on the definition, will be 0 to infinity. E to the power minus st. This is 1, so it's just this dt. How do I get the antiderivative of this guy? Anybody know the antiderivative of this?
Negative 1 over 5 e to the negative 5t.
Negative 1 over s. It's an s, not a 5, sorry. Is it okay? That's the antiderivative. It's an s, not a 5. It's just my handwriting is terrible. Okay. You plug in t equal to infinity. You plug in t equal to infinity. As long as s is bigger than 0, okay, as long as s is bigger than 0, okay, so let me just do this then. Minus e to the power negative s. Okay, can you see that as long as this guy is bigger than 0, so this one will goes away when you plug in infinity, it's going to be 0. So it will be 0, subtract, you put in the 0, would be negative 1 over s. So this guy should be 1 over s as long as s is bigger than 0. Do you guys follow that? Yes or no? So we now know that.
T goes to infinity.
Say that again. I cannot
Oh,
hear
so
you.
as t goes to infinity, the e to the negative st goes to 0. So we're just left with a negative 1 over s.
Yeah. So it will
Okay.
be 0 minus negative 1 over s.
Yeah, got it. Thank you.
You're welcome. Okay, so we know that the Laplace transform of 1. Okay. So I'm going to build a little table somewhere, maybe somewhere here. Hopefully we can do a bunch, some of this today, more than one. F of t, Laplace transform of f of t. When this is 1, this will be 1 over s. We're just gathering some result, okay? Another example. How about this? E to the 3t. And Laplace transform of e to the 3t will be 0 to infinity minus st. F of t is e to the power 3t dt. Okay. And then this will be similar to what we had before. Okay. E to the power minus s minus 3. S minus 3. Infinity is 0. 0 minus s bigger than 3 is to make sure that infinity put in here you get 0. Okay. So I now have the Laplace transform of an exponential function. Okay. E to the power 3t. This one will be 1 over s minus 3. Is it okay? Up till here. Are we okay up till here? Yes? No?
I am, yeah.
Okay. So what happens if I don't use a
That's
3
right.
here? Okay, if I don't use a 3, I use a constant a here. What do you think it changed to? Would the
1 over
3
s minus a.
s minus a? Very good. This is more general. It's nicer. Okay. So we are going to build up like all these standard functions. You get the Laplace transform, so that when we do those picture earlier, you try to solve the differential equation. When you take the Laplace transform, it's easier. You immediately know some of these answers. Okay. You don't have to do it every single time using the definition. Okay. We don't really use the definition that much. Okay. The next one. The next one is this. Okay. Before that, let me do one thing first. Okay, I need to do a property. Linearity property. We say the Laplace transform of alpha ft plus beta gt is the same as alpha Laplace transform of f of t plus beta Laplace transform of g of t. I'm not going to. Proving is very easy because from the definition of the Laplace transform, the integration has this type of property. Integration is linear. Integration, when you integrate two functions, the sum of two functions, you can split them as individual integrals and add. And then also in integration, you can pull a constant out. And that's why you Laplace transform of individual functions, and then you also can pull the constant out. So Laplace transform has this linear property, okay, that we will use all the time. Now, we can talk about this, e to the power minus IKT. Now remember, this guy is actually what? Cosine KT plus I sine KT. Is it okay? You guys know what I'm talking about? This is Euler's formula, right? Remember that in earlier sections? Now here, this one, if I apply this, this will be the value of A. This will be the value of A. Okay? And then I will end up with 1 over S minus negative IK, which is 1 over S plus KI. Here, I want to compare this with this, okay? Because this other side is Laplace transform of cosine KT plus I Laplace transform of sine KT. And I want to eventually, this is real part, imaginary part. I want to write this as real part and imaginary part. But the I is at the bottom. I is at the denominator. How do I get rid of the I in the denominator? Any suggestion? Like 1 over 2 plus I, how do you get rid of the I in the denominator? You guys know what I'm talking about? You can multiply the top and bottom by
Conjugate.
the conjugate. Exactly. 2 minus I, 2 minus I. And then you will get rid of the I in the denominator. So I am going to do this. S minus Ki, S minus Ki. And then I end up with S minus Ki on the top. What would the bottom become? It's the difference of two, the formula for difference of two squares is x plus y times x minus y become x squared minus y squared. This will be s squared minus ki squared. But I squared is -1, so it's s squared plus k squared. So now I can look at this as the real part, which is this guy, plus minus. The real part. I make a mistake somewhere. What did I do wrong? Oh, Jesus Christ. This is so bad. I'm really sorry. I make a mistake here. I shouldn't have the minus sign here. With the minus sign, it will become minus. So I just get rid of this minus sign. I'm very sorry. Okay, so there should not be a minus sign there. So this minus sign go away. So this become minus. Okay, so this become minus, and those two become plus. Okay. Okay, so now it's good. Sorry about the mistake, but I just fixed it. You have to go back and fix yours. How are we doing up to here? What does it say? What it's saying here is that this guy is equal to this. And this other one is equal to this. Okay? So what we have is that you don't have to know how to do this, okay? We just need to derive the formula for you once. Laplace transform of cosine kt is s over s squared plus k squared. Laplace transform of sine kt is k over s squared plus k squared. Okay? That's the bottom line. So here you have cosine kt will be s over s squared plus k squared. Sine kt will be k over s squared plus k squared. Is it okay? I'm sorry about that mistake I made. I somehow put a negative there. How are we doing up to here? Maybe if I do some example will be better. Okay? Hopefully it will become better. Okay. Erasing this. The bottom line is this. Okay, you can use those. That's the bottom line. Laplace transform of 4e to the power 5t minus 10 sine 2t. You guys help me with this. What is the answer? Everything is here. 4 times. What is the Laplace transform of e to the power 5t?
1 over s minus 5.
Subtract 10. Laplace transform of sine 2t. Sine 2
That'd be
over
2 over s squared plus 2 to the power 2. 4.
okay. And then you can write this as 4 over s minus 5 minus 20 over s squared plus 4. Okay? Next. Okay? I want to know this. I want to know let me look at this picture here, f of t. Okay. I'm going to just use this double arrow like this. This is called a transform pair. So basically this guy, the transform will be f of s, and the inverse transform of this will be this. Okay, so this is my f of s. This thing here is my f of s. Okay, it's just a notation. Usually the little f is for the time domain, the capital F is for the s domain. Okay. Now, what I want to do is the following. I want to see what happens if I differentiate this guy. If I differentiate this guy, okay, over here, what happened to this side? What happened to this guy here? I take the derivative of the S domain, and I want to know what happened to the what corresponding action is it on this function f of t in the time domain. Okay, so this is what we're going to do next. Okay. This is f of s. I can actually erase this one here. So what we are trying to do is see what happened to the derivative of the transform. Okay. You have the transform, which is defined as this. And you are trying to do the derivative of this. Maybe just write f prime there. Okay, f prime is the derivative. Okay. You guys follow up to here? I'm trying to muck around with this. Okay. Eventually we'll answer this question. So what is this here? Now, these are limit of integration. Remember, this is a function of s. Okay. Now we are I'm putting the integral. Okay, I'm sorry, not the integral. Putting the derivative inside here. Basically, swapping these two, swapping the order of these two. Okay. dds of e to the power minus st ft, and then dt. Now you need to understand what's going on here. When you do dds, I'm treating t as a constant. I'm treating t as a constant and then taking this derivative. After taking this derivative, I have something in terms of s and t. Okay. And then I do the integral with respect to t. Okay. So to be more specific, this one, just to emphasize that this is differentiating with respect to s and keeping t constant. Okay. This whole thing here. So I'm going to change the notation a little bit to partial derivative. Do you guys know what I did?
Can you explain that one more time?
Okay.
Sorry.
No problem. I'm swapping the order. When I'm putting this thing inside here, I'm going to just write another step. Okay. dds. But you understand that after I swap this order, when I take the derivative, it's respect to s. Okay, because if you look at this whole chunk, after you do this integral, the t is gone, nothing left, only s is left. That's why it's dds. Okay.
Okay.
When you swap this in, this guy here, you need to make sure that you understand that when you take the derivative, you keep the t as constant.
I got it.
The t there.
I got it. Thanks.
No problem. So that's why here is actually partial derivative. Okay. Now let's try to take the derivative of this thing. Okay. Let's compute this part.
Professor.
with respect to s though, so it's not really that complicated, this derivative. The ft is now a constant, so the ft will stay because it's a constant. The ft actually stays. Here, parcel this parcel s with t as a constant, you're going to use what rule?
Chain rule.
Chain rule. Chain rule, you'll pull the minus t out, e to the power minus st, because it's with respect to s. Okay? And this one here is the Laplace transform of this function. Is it okay?
Professor,
Yeah.
could you have done the integral first with respect to t and then take the derivative with respect to s, or?
It's harder because you don't know what f of t is. It's general.
Okay.
You know what I'm saying?
Yeah.
Because f of t is completely general. Okay, so now we kind of answered the question earlier. If this is f of t and this is f of s, when you take the derivative here, differentiation, okay? When you take the derivative, okay, then you get f prime s, and this other side, okay, is the, now because here you're going backwards, right? Going backwards. So this other side, okay, this is f prime t, Laplace transform of this. So the inverse transform going backwards is minus t ft. Is it okay? So differentiation over here is multiplication by negative t. Differentiation in the S domain is the same as multiplication by negative t in the time domain. Usually, of course, this is completely correct, but usually people would like to do this like this. And just over here is multiplication by t. So this one becomes tft. And the other side will be negative differentiation. Okay, so -1 times differentiation. So basically it's negative f prime fs. These two pictures are essentially talk about the same thing. It's just where you put the minus sign. That's all. But people usually use this one a little bit more. Okay, we will focus more on this. How are we doing up to here? We're doing a lot. I am going to do this. Now this is 1 will give you 1 over s. So t will give you what? Can we apply that formula? Apply this diagram with this one as 1 and this one as 1 over s. Then this guy will be t times 1, which is t. And what will be the other side? The other side is the negative of the derivative of this. You guys know what I'm doing? I'm plugging some of this result into here to get some more formulas. Okay. If you start
The
with
1 over s squared.
1 over s squared. right? It's s to the power minus 1. You take the derivative, you have a negative 1, but this is negative. So become 1 over s squared. Is it okay? Are you still with me? You can do it one more time. You can do it one more time. Become t squared here. So okay, let me just write it out like this instead. Okay. So we have 1 will correspond to, okay, I am going to erase this. I don't need it anymore. I'm going to draw some kind of tower here. 1 correspond to 1 over s multiplied by t. Okay, then this become t. This become 1 over s squared. What happens if I do it again, multiply by t again? Multiply by t again, you get t squared. And this guy, what do we do here? This is s to the power minus 2. You differentiate this, what do we get?
1 over s cubed.
Minus 2 s to the power minus 3, right? But you have to put the negative. It's negative times the differentiation. So this guy become 2 over s cubed. Can you guys see that? Yes? 2 to the power. Can I do it one more time? So this one will be, can you see this is 3 times 2 s to the power minus 4? Are you guys able to see that? No? Yes. It just keep differentiating. It just keep differentiating on the right hand side. You differentiate and then put a minus sign in front. S to the power minus 1, you differentiate and then put a minus sign in the front, you become this. And then you do this again, become this, do this again, become this. I mean, you can keep going, right? So what do you think it will happen after a while if this is t to the n?
Factorial.
N factorial. N factorial divided by
S to the n minus or plus 1 factorial.
s to the power
N plus
n
1 factorial.
There's no factorial.
Oh, right. No, sorry. Yeah, no factorial. Sorry. But n plus 1.
It's okay. So what I'm trying to say is that here, t to the power n is going to be n factorial s to the power n plus 1. Of course, when n is equal to 0, we'll give you this. N equal to 0 will give you this. It's okay? So this one is actually, this one, the first one is a special case of this one now. Is it all right? It's a lot. I am going to just do one more thing since I'm really there. Okay, I'm going to build another tower. Using this, e to the power at 1 over s minus a. You multiply by t, and then this guy will be the derivative. What's the derivative of this guy? the derivative of this guy, and then you take negative. Can you see this is 1 over s minus a squared? Chain rule. Chain rule this guy. Yes?
Yeah.
And then do that again. Here, s minus a to the power minus 2. And then you end up with minus 2, and then s minus a to the power minus 3. Okay. And the minus 2 is going to be minus, it's going to be positive. A similar pattern to this guy. Okay, similar pattern to this. Okay, and you can keep going. And then after a while, you will have this. And this is going to be very similar to this, except what? So you will have n factorial. The bottom, except the bottom is slightly different. What will be the bottom? Instead of s to the power n plus 1, it will be
S minus a n plus 1.
yeah, s minus a to the power n plus 1. Okay, so we also have this t to the power n e to the 8t, the n factorial s minus 1 a to the power n plus 1. Of course, this guy encompass these guys. So if you take this guy, you set a equal to 0, you will get this one. Okay? Okay? You set a equal to 0, you will get this guy. You set n equal to 0, you will end up with this. It's okay? You set both n and a equal to 0, you end up with this guy. So basically, it's this formula together with this two. Okay? So this will encompass the other ones, I mean, but these are also useful in the sense you use it all the time. But this one look more complicated, but it's more general. So we did quite a bit. So we're building up our table now of Laplace transforms. This is all I have.
Professor, do you mind moving over just a little bit?
Yeah, I won't really erase it. I will just wait.
Oh, you're blocking a little bit of the board.
Oh, I'm blocking. Sorry. Okay. I do that all the time. Even face to face, I do that all the time, right?
No, it's just now it's the board smaller, so
The board is a lot smaller.
catches you on the board behind.
Yeah. The board is a lot smaller. I wish I have more board space.
It's all good. You're doing your best.
You're doing a great job.
Thank you.
We thank you for this.
I try to make it as close to the face-to-face lecture as possible. But I know it's a lot harder for you to learn like this. I'll review this, what we've done. I've summarized what we have done on Tuesday a little bit, okay, before we proceed. We're doing pretty well. It's just this class has a lot of calculations. So any questions before we sign off? Okay. We are basically done. Okay. So if you are not, I won't sign off yet then. Okay. I'll just like whatever you want to copy, you can copy. But we are basically done today. So have a good weekend. Okay.
You too, Professor.
Thank you,
Have a
too.
great day.
Professor.
Thank you, Professor.
Bye.
Okay. Keep safe. Okay. Bye. Thank you.
Quick question. Is your a laptop like sitting on top of like books or something?
The laptop is sitting on a stand.
Oh,
No.
okay. Is it possible to like raise it up so that the board is a little bit more like flat? Because it's like the more real estate of the screen the board can take, the better. Yeah.
Okay. Yeah. I can try that next time. I mean, I can put it on the board on top of the stand.
Okay.
Yeah.
Okay.
It's a little bit distorted, you are saying.
Yeah. Like the top is a little bit farther away than the bottom.
Right.
Yeah.
Okay. Maybe let me test it. Hold on. Okay. You can tell me. I'm testing. How much better is it?
Can you move it a little bit closer to the board?